So welcome students to this video, and in this video we are going to continue our study of exponential of a matrix. So essentially what we looked at in the last video is, if you have a matrix A, okay, given, and with the distinct eigenvalues. What are the eigenvalues? Lambda i's and alpha p plus I beta p. Okay, so and where I ranges between 1 to k, okay, and d1 d2 dp, so p lies between 1 to, let's just write it as, that is n cross n matrix, right? So n minus p, okay, n minus p, clear? Okay, now what we are trying to suggest here is this. See that if A has maybe a complicated matrix, right? But if it has distinct eigenvalues, then you can have a change of variable. Yes. So this actually determines the change of variable t, such that T inverse AT will look like an very much like a diagonal matrix. May not be fully diagonal, because you see this d1 d2 dp, these are like block matrices, okay, but more or less very much like a diagonal matrix. Okay, now this form, so let me make a small remark here. The form which we got, this form, the above form is called the canonical form of A. Canonical form of A. What does it mean? It means that you can always have a change of variable which actually reduces a very complicated looking matrix to a very like a diagonal matrix. Okay, right. Now the question is this: why are you suddenly interested in canonical form? Why are we interested in canonical form, right? Interested in the canonical form. Now we already know that form. You see, we know that x prime equals to a x and x0 equals to x naught. Let's just look at this equation. Yes, this equation admits a solution, right? Admits an unique solution. And unique solution, where unique solution? Unique solution. And what is the unique solution? It is given by xt equals to e to the power at times x naught, right? That's the unique solution. So this holds for all t in R, right? Yes. Now you see, if we want to explicitly calculate what the unique solution is, so basically e power at, if we can calculate that part, then you just multiply it by the vector x naught and we are done, right? Okay, so how do you calculate e power at? So how to calculate e power at? That's the question, right? How to calculate the exponential? Calculate e power at, right? That's the question, right? Now you see, if A has distinct eigenvalues, okay, so case 1, if A has distinct eigenvalues, then what happens? So A admits distinct eigenvalues, okay. So you see, A can be written as, so there is a T such that T inverse AT can be written as this diagonal matrix, okay. So okay, so you see what happens is this, therefore, and let's just call this matrix as B for now, okay, the diagonal matrix, let's just call it to be B, B. So B is a nice matrix, let's just put it this way. So you see, therefore, e power at, yeah, how does it look like? It is nothing but, you see, if T inverse AT is B, okay, so you see, if T inverse AT, so there is a T such that T inverse AT is B, right? B is like a very much like a diagonal, almost diagonal, let's just put it this way. So you see, what is A? A is T, B T inverse, right? A is B T, and then what is e power AT? It is nothing but e power T B T inverse times small t, right? So, and we know for, that when we were doing matrix exponential, we talked about this property of matrix exponential. It is nothing but t e power b, okay, t and t inverse. This is what we are going to get, right? So you see, t and t inverse, once you, if one can find out what t is, what t inverse is, okay, so you just have to calculate what e power bt is, Clear? So once you know what e power bt is, then you can just put everything together and you can calculate e power at. Okay. Now the main question is this: how does one find e power bt? That's the main question. Okay, and then we will solve one problem and I will show you how to get the answers. Okay. So now let's look at this. See, the thing is, how to find? See, why this canonical form is important. What is e power bt? See, b looks like what? For example, without going into like a general case, let me give you an example that will make everything clear. Okay, so an example. Okay, see, if everything is real distinct, lambda 1, lambda 2, lambda k, then you can of course understand what is going to happen. Okay, so let me do it for lambda 1 real distinct and 2 complex conjugate. Okay, so basically for a 3 cross 3 matrix, let A, which is a 3 cross 3 matrix, admits the eigenvalues alpha, okay, and beta plus minus I gamma. Clear? Okay, so 3 eigenvalues are there. One is alpha and one is beta plus minus I gamma. Those are the 3 eigenvalues. Okay, of course alpha is in R. Yeah, of course that is assumed. Yeah? Now you see what is happening is this. In this case, what is the the T inverse at, that is B. So in this case, therefore B will look like this. See, it will look like alpha 0 0. So the first corresponding to alpha, it will be alpha 0 0, right? Now corresponding to beta, you see it will be alpha beta minus beta alpha. Okay, so sorry, this is beta gamma. So beta gamma minus gamma beta. So beta clear, and then what is it? This is gamma minus gamma. This is going to happen. Is this clear? I hope this is clear. Okay, so in this case, this is the matrix which you are going to get after the this almost diagonal matrix which we are talking about. Now you see, what exactly does it mean? If this is the matrix, let's just say this is the matrix. Okay, now one way of looking at it is this. Let's say that you are looking for this problem, right? X prime, we are looking to solve this problem. X prime equals to x. We are looking to solve. Clear? Now you see what does it means? X prime equals to a. What is a? A is nothing but, you see, a is nothing but T B T inverse. If we can do something like this, then it is nothing but T B T inverse times x. Okay, that will imply that T inverse times x whole prime is nothing but B T inverse of x, right? See, if we take this T on the other side, it is T inverse, and since T is basically a constant matrix, I can take it inside the derivative. Okay. Now, if one defines y to be nothing but T inverse of x, then let's call it 1. Then the equation, then the system 1 reduces to what is it reduced to? Y prime equals to by. Yeah, and you see the initial data is x0 equals to x0. Okay, so in this case y0 will be T inverse of x0. So T inverse acting at x0. Clear? Okay, now the any solution of this problem, you see, and yt, what is yt? Yt is nothing but e power bt times y at the point 0, which is T inverse of x0. Clear? Okay, so you see, if we can calculate what is e power bt, and of course if we know what is t, then we can of course know that what is y, and then once we know what is y, then we know what is x, because y is nothing but t inverse of x. So in this case, then you see, if y of t is this, then that will imply that t inverse of x is nothing but e power bt times t inverse of x naught, right? So that will imply x of t is nothing but t e to the power bt t inverse acting at x naught. So you understand? So it is very important to calculate e power bt. You see, this is the same thing which we did here. Okay? So that's the idea. Now, another beautiful thing about this canonical form is this. See, this, if we can reduce this form, what happens is solving. So let's say we want to solve this. We have, or we want to solve. Solve y prime equals to by, right? So let's just call y to be y1, y2, y3, 3 cross 3, right? Okay, so it means y1 prime, y2 prime, y3 prime is nothing but that matrix, right? What is the matrix? You see, it is alpha 0 0, alpha 0 0, 0, beta, gamma, 0, minus gamma, beta, right? And then y1, y2, y3. See, this is what we are going to get. Now, if you write down properly, it means y1 prime. That will imply that these are the three equations which you are going to get. Y1 prime equals to nothing but alpha times y1. Y2 prime is nothing but beta times y2 plus gamma times y3. And y3 prime is nothing but minus gamma times y2 plus beta times y3. Okay. Now, the first equation is very easy to solve, right? So, let's call it 2, 3, 4. So from 2, what do we get? From 2, one gets y1 of t is nothing but e to the power alpha t, right? Of course, a constant is there. So let's just write it as c1 times e power alpha t, and c1 is in r. And from 3 and 4, from 3 and 4 and 4, you see, if you just think about it this way, this is a system of 2 cross 2 equation. There is no y1 involved here. Okay, so you have this system y2 prime, y3 prime equals to nothing but beta gamma minus gamma beta y1 y2. Okay, so what is the solution here? Oh, sorry, y2 y3. Okay, so the solution y2 y3, this will be nothing but e power this matrix, right? Let's call this matrix as C, e power C times, okay, e power C, one second, C times T, right? That will be the solution. Yes. So if we times, of course, that constant some matrix, let's just call it D, which is a n cross 3 cross 2 cross 2 constant matrix. Okay, constant matrix. Sorry, it's not 2 cross 2, 2 cross 1. It's just a constant part that I am writing. Now you see e power ct. Now, if you remember, we talked about this sort of equation, right? Beta, this sort of exponential, beta gamma minus gamma beta, and we saw how to calculate that exponential. Okay, if you remember how to calculate that exponential, what we found out is this from that when we calculated that exponential essentially is this is nothing but e to the power beta, right, cosine gamma minus sine gamma, okay, sine minus sine gamma and cosine gamma. This is what we got times a matrix D, 2 cross 1 matrix constant. Okay, so this is what we are getting. If you remember, we did it in the maybe another 2 videos back, we just calculated this thing. Okay, again, if you are not convinced how we got from here to here, let's just do it in another way. That will be a more easy way, but I am not going to calculate the exact same thing. What I am going to do is I am going to show you how to do this part, and then you can do it yourself. Okay, this is another method of looking at the exponential of this particular thing. So you see, let's say that let a matrix P is nothing but alpha, okay, and gamma or beta. Let's just call it beta, gamma minus gamma, right? That's the matrix given to us. You see this matrix. I want to calculate the exponential. Yes. Now, how do you calculate? You see, I can always write it as beta 0 beta plus 0 gamma minus gamma 0, right? That will be beta times identity plus gamma times this matrix 0 1 minus 1 0, right? So you see, therefore if we want to calculate e to the power p, let's say, okay, what is it? It is e to the power beta times e to the power 0 gamma minus gamma 0, this matrix, right? Okay, beta I, sorry, e to the power beta I times this. Okay, now you see what is this matrix. So e to the power beta is very easy to find out, right? What is e to the power beta I? It is nothing but identity plus beta times identity square I plus beta times beta square by 2 factorial, okay, I square, and it goes on like this times e to the power 0 gamma minus gamma 0. Clear? Now this is nothing but exponential beta, right? This is exponential beta I. Okay, how do I put it? So let me write it this way. See, this is nothing but 1 0 0 1 plus beta 0 0 beta plus, you can write it like this. So you do understand this 1 beta square, those things will come, okay, times e to the power 0 gamma minus gamma 0. So you see, this is nothing but e to the power beta, right, times e to the power 0 gamma minus gamma 0. You see, e to the power beta, that is why this e to the power beta is there. See, okay. Now the thing is, this matrix, we are just saying that this is nothing but this matrix, e to the power 0 gamma minus gamma 0. Okay, let's just calculate it. Let's see what happens. Okay, okay. Now e to the power 0 gamma minus gamma 0. What does it mean? It means, first of all, it is identity plus 0 gamma minus gamma 0 times there is nothing times, so this is plus 0. So let's calculate e to the power this matrix times t, because all of this is like e to the power pt. So this is t, this is t, okay, so that is always there. One second, I did some mistake here, I think. Yeah, so I forgot to write the t part here. Okay, so it is beta t, gamma t, this t part is there, this I forgot to write. Okay, so this t part is there, so please keep that in mind. I forgot to write it, but anyways, you do understand what is happening, right? So sorry, here there won't be a t plus this t plus goes on like this. Okay, so this is times t, this times t. Okay, the t, that part I forgot, but anyways, you do understand what I'm trying to say. Now you see, let's calculate this thing. See, 0 gamma minus gamma 0, 0 gamma minus gamma 0. Okay, if we calculate the whole thing down, what is happening is this will actually give you minus gamma square 0 0 minus gamma square, right? And then this is square. What about the cube? The cube is minus gamma square 0 0 minus gamma square times 0 gamma minus gamma 0, right? So what will happen if we are doing the second part, that is, okay, the third part, cube. This is minus 0 minus b cube and then b cube 0. Okay, let's do another one, the last one. Okay, now let's say 0 minus b cube 0 times 0, sorry, what is this? Is gamma, this is gamma cube, and then the last part is 0 minus gamma cube 0 times 0 gamma minus gamma 0. If we multiply it, you see you are going to get gamma power 4 0 0 gamma power 4. Okay, this is what we are getting. See, if you put it together, then what happens is r square is minus r square is minus gamma square 0 0 minus gamma square times t square by 2 factorial plus the cube part 0 minus gamma cube 0 t cube by 3 factorial plus gamma power 4 0 0 gamma power 4 4 by 4 factorial, and it goes on like this. Now you see what is happening is, what is the first term? It is 1, the second term is not there, minus gamma square t square by 2 factorial. Okay, the third term is not there, the fourth term is plus gamma power 4 to the power 4 by 4 factorial, minus, it goes on like this. That's the first entry. What is the the first row second entry? The first row second entry is 0, so the second is gamma, and from here gamma cube t cube by 3 factorial. Okay, and it goes on like this. Okay, and what about this term 2 1 is minus gamma t, okay, plus gamma cube t cube by 3 factorial plus gamma cube t cube by 3 factorial, okay, minus, it goes on like this. Okay, and what is this term here? The 2 2 term is 1 minus gamma square t square by 2 factorial plus gamma to the power 4 t to the power 4 by 4 factorial, and it goes on like this, right? Now you know this is nothing but sine and cosine. So essentially, if you write it down, it is nothing but cosine beta t, sine beta t, okay, and minus, this is minus sine beta t, okay, and this is cosine beta t. Clear? Okay, so you see this and this is essentially the same thing which I wrote here. Okay, these and these are essentially the same thing. Okay, so you see what I want you to do now is this. So there is nothing to check. I calculated everything. Okay, so anyways, so you understand how this is going to be calculated. So this is done. So this is how we calculate this part. Now you see what happens is, if you want to find out what is y1, y2, y3, we already got it, right? Y1 is this. So therefore I can write it like this. Let me put it this way, and in a red. What did we get? We get y1 of t, y2 of t, y3 of t. How does it look like? It looks like this. What is y1 of t? It is c1 times e to the power alpha t, right? What is y2 of t? See, this d is nothing but, let's say, c2 c3, some matrix, right? So it will look like this. E to the power beta t is always there, right? So c2 times e to the power beta t cosine gamma t plus c3 e to the power beta t sine gamma t. Okay, and what is the third expression? Minus c2 e to the power beta t sine gamma t, because you see this what is y3? Y3 is nothing but c2 times this, okay, plus c3 times this, plus c3 times e to the power beta t cosine gamma t. Okay, so you see we have the whole expression. Okay, so this is the solution, right? This is the solution. So this is y of t. So y of t can be written like this. See, y of t is nothing but this vector. Clear? Now once we get y of t, now the only thing which is required to show that what is t, how do you get such a t? So basically once you find a t, see, x of t is nothing but, see here, x of t is nothing but this. Okay, e to the power beta t, you know what is y of t? What is y of t? Y of t, see, y is t inverse x, right? Okay, so y of t we already got. Now if we just can calculate what t inverse is, we are done. Okay, so this we will learn how to do it, but let us do the the other part, that is the when there is a repeated root. Once we do it, and then I will do one example where all of this will be put together. Yeah, I hope this is clear why we are actually working with the canonical form, because it makes our life easier, okay, to deal with. Now as for the repeated roots, what we are going to do is, this is a little complicated issue, right? And we are going to do it for 3 cross 3, okay? And for this course we are only going to assume, more or less we are going to do 3 cross 3 systems, yes? So don't worry about it. Now for a 3 cross 3 system and having repeated roots, so let me just put it as a theorem, okay? Theorem. Let's look at what is the canonical form. So say let A be a 3 cross 3 matrix, okay? 3 cross 3 matrix for which lambda is the only eigenvalue, right? Eigenvalue, okay? Then what happens is, you can find, so there exists a transformation T, okay, change of variable coordinates, that is such that T inverse AT, clear, assumes one of the following form, assumes one of the following forms. So what are the forms? The first form is, it may look like this: 0 lambda 0 0 0 lambda 0 0 0 lambda, okay? So when is this case? Essentially you can just think, this is very much like intuition. The first case will be achieved when there is there is just one eigenvalue, but the thing is, for that eigenvalue you have 3 linearly independent eigenvectors, okay? So this actually for n cross n matrix also exactly the same sort of thing will happen, so you don't have to worry about it. So for n cross n matrix, if you have like for one eigenvalue, if you have like n linearly independent eigenvectors, then the corresponding matrix will look like this, okay? So what is it? Lambda times I, essentially, okay? Now if the other case is this, it should look like this: lambda 1 0 0 lambda 0 0 0 and lambda, clear? And the third case will look like this: lambda, okay? So you see, in both the cases, in all the cases, they are going to be triangular matrices, just like a different kind of triangular matrices, okay? The first thing is of course the easy one, the diagonal matrix, and this is like this sort of matrix, okay? So 0 0 0, okay, right? So let's look at the proof of this. Yes, proof. Now if you see, it all depends on basically the kernel, right? So let's say define the kernel of A minus lambda I, let's just call it as K, clear? If we call that as K and the dimension of K is 3, let's say, okay? So case 1, the dimension, okay, of K is 3, clear? So what does it means? It means A minus lambda I, okay? See, A minus lambda is from R3 to R3, right? As a linear operator, it is from R3 to R3, okay? So this acting on V is going to be 0 for all V in R3, right? Okay, so you take any vector, doesn't really matter what, okay? Since the kernel dimension is K, so basically what will be your K? K is the whole of R3. So essentially for any V in R3, you have A minus lambda I V equals to 0. What does that imply? Since this relation holds for all V, that will imply that A equals to lambda I, of course it has to be. There is no other option, right? A equals to lambda I, clear? And if A equals to lambda, you see, this is what lambda I is, okay? So the first case is trivial, and from this actually holds for n cross n also. It's not a problem, okay? It's the same thing, okay? Now comes the difficult two cases, okay? Case 2. Now let's say that the dimension of the kernel, okay? Dimension of the kernel is, let's say 2, yeah, 2. Now what happens is, let's call that, we define R to be the range of A minus lambda I. Clear? We just call it as R. Then, since dimension of K is 2, you do realize that the dimension of R will be 1. Why? Because A minus lambda is from R3 to R3, right? So, the rank nullity theorem says that the dimension of R has to be 1. That is quite easy to see, right? It has to be. Okay. So, now you see we claim that one is contained in another. Which one is contained in another? R is contained in K. Okay, bold claim that is. But the thing is, this is true. Why this is true? Let's see. That if it is not the case, okay, then you see there exists an element in R which is non-zero. Okay, so there exists V, let's say non-zero, in R, in the range. Clear? Okay. Okay. Now you see what did I want to show? R is contained in K, right? R is contained in K. Okay, so I start with a non-zero element in R. Let's call it a V. Okay, now you see A minus lambda I, okay, acting at V. Yes, this is in R. Clear? See, V, the vector V is in the range. So what does it mean? A minus lambda I times V should be in that set R, and R is one dimensional, that is given. You see, dimension of R is 1. So that will imply A minus lambda I times V will look like some mu times V, right? See, V is not 0 element, right, in R. And since the dimension of R is 1, we can think of the basis of R to be just containing V, right? Because V is non-zero. Okay, so I can just write it as mu times V, for some mu non-zero. Clear? Now that if that happens, then AV will look like what? Lambda plus mu times V. Clear? Lambda plus mu times V. So you see what happened is, then we actually, and this is nothing but the eigenvalue problem. So we found out a new eigenvalue which is given by lambda plus mu. Okay, which gives us a new eigenvalue given by lambda plus mu. Okay, but we assume that lambda is the only eigenvalue. Okay, so lambda plus mu has to be equals to lambda. That will imply mu equals to 0. But here we have assumed mu not equals to 0. So therefore, R has to be contained in K. Clear? Very simple. It's not very difficult to see this. Okay, so let's look at the next part. So R is contained in K. That's fine. Now what happens? So you see, let V1, I will start with another element V1 be non-zero in an R. Okay, non-zero. Okay, now you see, since V1 is non-zero in R, so it is in K because R is contained in K, we just showed. Yeah, and V1 is an eigenvector. Right? Why? Because if V1 is in K, then A minus lambda times V1, you see, V1 is in K, A minus lambda I times V1 is going to be 0, right? So V1 has to be eigenvector, right? Okay. So that implies, okay, I should write it here, A minus lambda I times V1 is 0, right? Okay. If V1 is in K, this happens, okay. So, okay, that is fine. Now, since again V1 is also in R, right? That's our assumption. V1 is in R. Okay, that will imply there exists a V2 in R3 minus K. Okay, with A minus lambda I times V2 is V1. Yes. So you see K, what is the dimension of K? It is 2. Right? That is what our assumption is. See, dimension of K is 2. So essentially you can of course find a non-zero element V2, let's say. Yes, which lies in R3 minus K. And since V1 is in R, you can always find A minus lambda I times V2 to be V1. Yeah, you can always have that element there. That is always true. Okay, right. Now you see K, where is it? Yeah. So now what am I doing? So since V1 is in R, you can of course find a V2 which is in the R3 minus K, so that this is happening. Okay, so this is fine. Now you see, okay, so since the dimension of K is 2 now, okay, then we can choose another element V3. We can choose V3, okay, in the kernel K such that V1 and V3 are linearly independent. Clear? See, V1 is in R, right? So V1 is in K also. I am choosing, since the dimension is 2, of course I can find another element in K such that V1 and V3 are linearly independent. Okay, since the dimension is 2. Okay, now you see V3 is also an eigenvector. Also, V3 is an eigenvector. Right? Okay. So now what happens is you choose a change of coordinate. What is the change of coordinate? Now choose this change of coordinate. T of Ej is nothing but Vj. Okay. For j equals to 1, 2, 3. Clear? If we do that, then you see what is happening to T inverse AT. Let's just see. Therefore, what is T inverse AT? This matrix. It is nothing but T inverse A, T acting at E1, right? And then T inverse A, T acting at E2, and then T inverse A, T acting at E3, right? That's the matrix. So you see, T of E1 is nothing but V1. A of V1 is nothing but, what is A of V1? A of V1 is nothing but minus lambda V1. Now T inverse of minus lambda V1 is lambda times, you see, this is lambda times T inverse of V1. T inverse of V1 is nothing but E1. Okay, so E1. Clear? So E1 is 1, 0, 0, right? So we can write it as lambda 0, 0. Clear? Okay, again, T of E2, what is T of E2? It is V2. Okay, T of E2 is V2, and V2 is what? You see, now A of TE2 means A of TE2 is A of V2. A of V2. A of V2. What is A of V2? A of V2 is nothing but V1 plus lambda V2. Lambda V2. Right? Now, you see T inverse of V1 plus lambda V2 is T inverse of V1 plus lambda times T inverse of V2. Right? T inverse of V1 is E1 plus lambda times T inverse of V2 is E2. So, it is 1, 0, 0 plus lambda times 0, 1, 0. So, it is 1 lambda and 0. Clear? And similarly, last one, if you just calculate it, it becomes 0, 0 lambda. Why? Because you see, the last one is V3, which is again an eigenvector. So, essentially the same sort of this thing will happen with E3 essentially. Yeah. Okay. So, this is the thing. So, you see, this is the second part. Clearly, this is B part. Okay. I hope this is clear. Now, let's look at the third part. Okay. So, now the case 3 is the dimension of K is 1. Dimension of K is 1. Okay. And then what happens is, what is the dimension of R then? Dimension of R is 2 then. Rank nullity theorem again. And then, as earlier, we'll claim that 1 is contained in another. You see, since the dimension of R is 2, K is contained in R. This is what we will, claim. Okay. We have to prove that. We did not prove it, but this is our claim. Okay. So, if this is not the case, so let's say if this is not the case, then A minus lambda I times R equals to R, right? Yes, if K is not contained in R, then A minus lambda I times R has to be equals to R. Okay, and A minus lambda I R is invertible on R, right? On that range it is invertible. Okay, it has to be, right? So thus, if you have a vector V which is in the range, okay, there is a unique W in the range, such that A minus lambda I times W has to be equals to V. Clear? So therefore, what is AV? AV can be written as A minus lambda I times W. Clear? V is A minus lambda I times W, so I am just replacing it. Now this is nothing but A square minus lambda A times W. Okay, that is nothing but A minus lambda I times AW. So I wrote it like this. Clear? Okay. See, what this shows is if V is in R, right? If V is in the range, then AV is also in the range. That's what it is showing. See, if V is in the range, AV is also in the range, right? Okay. So what it shows, and that implies, therefore, it implies that A preserves the subspace R. Subspace R. Okay, right. Now A, if it preserves subspace R and it does this, so you see definitely A has to be an eigenvector in R, right? So therefore also that will imply that A has to be an eigenvector in R. So has to have eigenvector. Let me phrase it like this: has to have an eigenvector. Has to have an eigenvector in R. Clear? Okay. Then that will imply that K has to be containing R, and which is a contradiction. Because we have assumed that K is not contained in R, right? So that's a contradiction, and this follows. Okay. So now what we are going to do is we are going to claim the second claim. This is a complicated situation here for this. Okay. The second claim is this: A minus lambda I of R is nothing but K. Okay. Now why is it? This is not a very difficult thing to see. See, A minus lambda I of R is one dimensional, is 1D. Okay, one dimensional. Why one dimensional? Because you see K is contained in R, right? See here, this is the claim which we proved earlier, right? K is contained in R. K is contained in R. Okay, so of course A minus lambda I times R is one dimensional, since K is contained in R. Okay. Now let's say if A minus lambda I times R is not the same as K, then there exists a non-zero vector V, non-zero, okay, which is contained in K, for which A minus lambda I times R has to be look like T times V, because it's one dimensional, right? T times V. T is in R, let's say. Clear? See, here we have assumed the dimension of K is 1, right? So that is why A minus lambda I times R has to look like T times V. Clear? Okay, so if this is the case and T is not 0, then that will imply that You see, okay, one second, TV clear. Now, okay, one second. Yes, a minus lambda I times r should be TV, right? Yes, that is what we are going to get. Okay, but you see, a minus lambda I times v should be equals to t times v, right? For some t non-zero, it should be equals to t times v. That, and therefore what happens is a times v should be equals to t plus lambda times v. Yeah, you take this thing here, then it works, right? And then what happens is you are going to get a new eigenvector. You see, t plus lambda, getting a new eigenvector, which is a contradiction. New eigenvector, eigenvalue, sorry, eigenvalue. Okay, now this is a contradiction, clear? So therefore a minus lambda I times r has to be equals to k. Okay, now we are more or less at the end of the proof. So now what we are going to do is this. So this is fine. Okay, so see, let v1, we will start with v1, which is in the kernel k. Yeah, so this is an eigenvector. Okay, so be an eigenvector for a. Okay, so what will happen is this. So we can say there exists v2 in r, right, such that a minus lambda I times v2 is v1. Yes, see, k is one dimensional, r is two dimensional, right? So essentially what is happening is this: you can always get, and r is the range, right? So you can always get a v2 in r such that a minus lambda I times v2 has to be v1 here, and 1 is contained in other, k is contained in r, right? So that's happening. Now since v2 is in r, okay, there exists a v3 then such that a minus lambda I times v3 is v2. Okay, so that will imply that a minus lambda I square times v3 is v1. Clear? Yes, and you can see it's very easy to see, so please check this part. Check that v1, v2, v3 are linearly independent. Okay, that's just by the construction, it is like that only. Yes, so you define your t as t of e1 to be ei to e vi, okay, for I equals to 1 to n, 1 2 3, okay, and therefore t inverse at, okay, this e, again I want you to check t inverse at. What will this be? It is, the first thing is t inverse at acting at e1, right, the first column. Second column is t inverse at acting at e2, and the third column is t inverse at acting at e3. Okay, just do exactly the same sort of thing what we did here. Okay, if you do it, you see v1, this is if you calculate it, you know what v1, v2 and v3 does. Okay, so if you calculate the whole thing, you will actually end up getting this lambda 0 0 1 lambda 0 0 1 lambda. Clear? So you have to check this part. Check. Okay, so this is what happens when, if you have a 3 cross 3 matrix with a repeated eigenvalue. This is actually something which is called the canonical form. This is the canonical form. Okay, so canonical form is, you can reduce it either in one of those 3 forms and you are good to go. So any one of those 3 forms will work. Okay, so what I am going to do is, since this a particular example is little difficult, let's just do a small exercise, how to calculate this. That will make life easier, right? So first of all, let's just assume a matrix A of which is 2 0 minus 1 0 2 1 minus 1 minus 1 2. Okay, it is very easy to check that lambda equals to 2 is a repeated eigenvalue. Eigenvalue. Okay, and of course you can always get a one eigenvector out of it. That's not a problem. Okay, so for lambda equals to 2, v1, let's call it 1 minus 1 0 is an eigenvector. Okay, now the thing is this, see, I have 2 is repeated thrice, right? 2 2 2, but the thing is I only have one eigenvector. Yes, and since it is just one eigenvector, it is independent. It's not a problem. Okay, and since this is non-zero, it is independent. Now the thing is this, I need to get another 2 eigenvectors. Okay, how am I going to get it? Okay, so this is the procedure to do it. Please remember this. Okay, so first of all, we compute this. You start with a, right? So we compute a minus 2i square. Clear? Let's just compute it. If you compute it, it becomes 1 1 0 minus 1 minus 1 0 0 0 0. Clear? Okay. Now the thing is this, I am going to find out a vector v3. Now the thing is this, how do you get, I want to get v1 I already got, want to get v2 and v3. Okay, so see, I want to, so we'll choose v3 such that a minus 2i square v3 is nothing but v1. So we are targeting v1. We want to achieve v1. Okay, and then a minus 2i square v3 is v1. This is what we are trying to do here. Okay, now see, if you calculate this thing, what happens is essentially 1 1 0 minus 1 minus 1 0 0 0 0. Okay, v3 1 v3 2 v3 3. So these are the 3 components of v3. Let's just assume that, and then that will give you v1. What is v1? This is our target. I want to reach v1 using square, the a minus 2i square. Okay, so this particular thing, what we are going to get, these are called generalized eigenvectors. Okay, right. So what you get is this v31 v32 and v33. We are going to get it as 1 0 0, right? Okay, and we also choose, okay, so we also choose a minus 2i times v3, okay, equals to v2. Clear? So essentially using this v3, okay, using this v3 we want to get a v2, right? Okay, so how do we get it? You see, so essentially what we are doing is this. See, first of all, I have a minus lambda I times v1 is 0, right? Yeah, lambda 1 is 2 here, so basically a minus 2i times v1 is 0. That's how we found out. Basically we tried to find out a v non-zero such that this happens, right? So solution was v1. That is what we got it. Now we use v1, yes, and we try to find it this way, that a minus lambda I square, we are trying to find a v so that this is equals to v1, right? That amounts to getting v3. Clear? Now we are going to start with cube, clear, of v. I want to target now v3 we already have. I want to target v3 here, and I need to find this. If we can find it, we will call it a v2. Okay, and then we are done. It doesn't have to be v1 v2, you can just change the numbers also, it's not a problem, but anyways we are doing it like this. Okay, right. So a minus 2i times v3 is v2, right? So what does it mean? It means that sorry, I should write it as, one second, I should write it as a minus lambda I cube v, what is it, v, yeah, so I have to find a v2, right? So I will target, I have v3, so I will target v3. Okay, now this is what, so you see, this is nothing but 1 1 0 minus 1 minus 1 0 0 0 0 times this matrix again, 2 0 minus 1 0 2 1 minus 1 minus 1 2 times v1, let's say v2, v3, 1 1 v, okay, let's just call this is v2, right? Let us just write it as v21, v22, v23, and the target is this 1 0 0, that's the target of v3. Okay, now if you calculate this, this is we are going to get v2 here. Okay, if you calculate it, you see it is 2, okay, and 0 0. So basically the first thing is you are going to get 0, and then minus 2 minus 2, yes, 2 4 v1 v2 v3. Okay, so this is 0 and the last part is minus 1. Okay, so this is how what we are going to get, v1 v2 v3 is according to this. Okay, this is how we got it, 1. Now what happens is we need to know, we need to write down the the diagonal element, how is it supposed to write down. Okay, so basically we let t of e1 to be v1, t of ei to be vi for I equals to 1 to 3. Okay, so what is t? T is nothing but 1 minus 1 0. Okay, see, t, if you remember, t is essentially nothing but this matrix. Okay, t acting at e1, t acting at e2, t acting at e3. e1 is what, 1 minus 1 0, e2 is 0 0 minus 1. Okay, 0 0 minus 1, and t acting at e3 is nothing but what is it, t acting at e3, 1 0 0 1 0 0. Okay, so therefore what is t inverse at? T inverse at, if you calculate it, it is nothing but so basically t inverse at acting at e1, which will be 2 0 0, t inverse at acting at e2, which is 1 2 0, and t inverse at acting at e3 is 0 1 2. Yes, so this is the t inverse at. Yes. Okay, I will give you some exercise for that, just for you to understand what's going on. So some calculations, it will be better for you to understand that, and then you can do this part. So it's not very difficult, it's just some calculation, you have to do it yourself, and then you can find this eigenvector. So this is the idea, the nomenclature here is, this is called generalized eigenvector. Okay, so with this I am going to close this video.